Okay, so this is the second of the videos on thermochemistry, and typically, again, when we deal with strand 11, it's dealing with the energy concerned with or involved in chemical reactions. But what I want to point out is that this isn't just about the energy associated with chemical reactions, it's also associated with chemical and physical changes. So take a minute right now and set up your page, only this time what we're going to do is we're going to make a graph. And the graph I used to make mine, I put 10 lines down and went all the way across here. So pause this a minute and make your graph. And I'm going to number my graph, and I'm going to start with negative 50 degrees Celsius down here on the bottom. So on the y-axis, I'm going to put temperature in Celsius, degrees Celsius. And on the x-axis, I'm going to put heat. And the heat's going to increase as we go this way. Okay, so negative 50, and I'm going to skip 2 lines and put 0 degrees Celsius. And I'm going to go by 50s, but I'm going to skip lines like this. And I can't put the C in there on a lot of those. But what we're going to do is we're going to basically look at water. So this is called a phase diagram. And every substance has its own phase diagram. So a phase change diagram, or change of state, but it's typically called a phase change diagram. So we're going to start off, and I'm not going to worry about getting the angles of the lines right, but just understand that the angles also, like the angle of the slope of the line, is going to matter here. So I'm going to put my first line here, and again, I'm just kind of eyeballing this. I'm not going to let it, let's see, I need to go up to 100. Okay, so it's really important where the lines are. So here is below 0. So since this is water, we know that the freezing / melting point of water is going to be right here at 0 degrees Celsius. And then we also know that the boiling point of water is at 100 degrees Celsius. And then we have a gas. So when I look at these things, I'm going to grab a different color here so it kind of shows up a little bit better here. So here we have a solid. And in this case, it's solid water, so we know it's ice. Here we have a liquid. And again, this is just what we call liquid water, since it's all about water. And then here we have a gas, and we call gaseous water steam. So we have solid, liquid, gas. So at this temperature, between negative 50 and 0 degrees, we have solid water, we have ice. At the temperature between 0 degrees Celsius and 100 degrees Celsius, we have liquid water. And then above 100 degrees Celsius, we have gaseous water. When we look at a phase change diagram, we can see the separate phases that water or that any substance is going through. Here is where we're changing phase. So this is where we're melting. If we're going to the right, it's melting. If we're going backwards to the left, we have freezing. And then up here, we have boiling. And if we go backwards, we have condensing. And my pen's running out. Condensing. So we have a phase change diagram. And if we get online, or if we pick up these things called books, we can actually tell that, hey, this section right here, somebody's done the work for us, and they know, well, exactly how much energy is associated with this process. So I'm going to put these little dotted lines down here. And in this case, for water, we have right here, when it's flatlined right here. So here we are, we're going to add heat to this. So we have ice, we're adding heat to it until it gets up to 100 degrees Celsius. We're still adding heat, but notice that the temperature flatlines, and while it's in the process of changing phase, all the extra energy that goes into it, all the extra heat that goes into it, is actually being used to take those molecules from the solid state to the liquid state. Remember that when molecules are in a solid, they're stuck together kind of but vibrating. So any extra heat, once they start vibrating so fast, it's actually going to be used to kind of pull them apart so they can get a greater range of motion. And the amount of energy to take this to happen, it's typically considered 1 mole of water, and I have to look on the chart, is 335 joules. Here, as it's heating up, and these numbers, and I'm sorry, I just lost it here. I think it's a mole of water. It could be 1 gram of water, but I'll have to go check and see. But there's a certain amount of water that we have that's going to be used here. And in this case, when you heat up this, let's say it's a mole of water, and we heat it up to the boiling point, that's going to take X amount of joules, or amount of energy, and those are 418 joules. And then at this stage, to get that same amount of water to actually boil and change to a gas, we're going to have 2,255 joules of energy. Okay, so I'm using that word joule. And a joule is the unit of measurement for energy. If we were doing the English system, it's a more common thing that you would know would be a calorie. So in the English system, but most people, even though we see calories on the backs of packages, we don't know how much that is. And so we see this, but it's like, yeah, it's a calorie, blah, blah, blah. I'll go to the school and create a demo for you guys so you can see exactly how much 5 calories it is, but I'll probably have to go into the schools one day this week and do that. So be on the lookout for a video that shows how much energy is in, what 5 calories of energy looks like actually. Okay, so when we see this phase change diagram, again, here it's in the solid form, here's in the liquid form, here's in the gas form. As it changes phase, the temperature stops changing. Now, the length of the line is equivalent to the amount of energy. That's needed to change phase. Again, change phase, change state, same thing. And then the other piece of information that I want you to know, and I'll move that up some. The other piece of information that I want you to know is that, again, during the phase change, when it's actively changing from a solid to a liquid or a liquid to a gas, the temperature flatlines. It stays the same. And so that's why you have this phase change diagram that looks like this. And it pretty much looks like this for any substance. It's just the temperatures are changing, the angles of the line change, but always at that point where you're changing phase, it's going to flatline. So you're still adding, you've got it on the burner the whole time here. So you've got it on the, if you're doing this on the oven, you've got it on the oven with the heat on the whole time. It's just that right into this stage right here is where it stops changing temperature. And you know this because every time I ask you guys what's the boiling point of water, you say it's 100 degrees Celsius. So when we come up here and look at this, well, here's the boiling point of water, and sure enough, it's 100 degrees Celsius. If you're here in the middle of it, on the side of it, over here at this point where you've got, let's say you've got 10 grams or 13 grams or 15 grams, it's still, when you stick the thermometer in there, 100 degrees Celsius. 100 degrees Celsius is that boiling point of water there. So when you talk about thermochemistry, it's not just about the energy and the heat associated with chemical reactions, it's also some other physical issues like changing phase and things like that. So we'll talk about that a little bit too later on in the next set of notes.